Good morning. I'm Karen Liu from Stanford. Welcome to Stanford. Some of you know that my lab has been very interested in studying human movements. Because if we can synthesize human motion, then we can have we open up the possibility to teach robots how to interact with humans or how to move like humans. But today I'm going to focus on this one topic, dexterous manipulation. In the past few years, we have seen rapid advances in robot dexterous hands, both in terms of sensing and actuation. And there's a lot of potential advantages for dexterous hand comparing to grippers. But if you think of every potential advantage, there comes with an array of challenges that we have to overcome. So for example, our hands are extremely flexible. We have a lot of degrees of freedom. But this comes with a price, right? Because when you have so many degrees of freedom, it makes kinematics very complex. And also we have to deal with very challenging dynamic constraints like wrench closures or friction cone constraints. And not to mention contacts when you have to deal with this contact space that's tend to be discrete and undifferentiable, combinatorial. That makes control and planning very challenging. So my student Albert came up with this solution, which combines both learning and model-based approaches. So he trained a generative model that can predict a finger placement, and then we can project that finger placement onto the manifold of kinematics and dynamic feasible grasp space using a bilevel optimizations. So here you can see that each row is a particular random seed that we request the generative model to give us a diverse grasp. So we get a lot of a diverse grasp, and then they are guaranteed to satisfy constraints because you have a model-based approach to make sure that that's the case. All right. So dexterous hands are also very versatile. So for example, if you want to build Lego structures, the way we would do it is we start off on digging this is kind of low, dig into a pile of Legos, and once you find the piece you want, you try to orient it and grasp it, and then eventually you want to put it on insert it into the baseboard of the target locations. So our hands can do all these in one sitting, right? Like we don't need to regrasp, we don't rely on external tools to do that. But this is a really challenging problem for robots because all those subtasks, they are small, but they're very diverse. And if you put all those subtasks together, this by default becomes a long horizon planning problem, which is difficult. So my students, Renpei and Chen, want to teach a robot how to play Legos. So our goal is to find a specific piece, let's say a yellow piece 1x2 from this piles of a Lego box, and then we want to put it in a specific location. And we identify, these are the subtasks that we have to be able to do in order to complete the task. A naive way to do is you just train RL policies individually, right? And then you put those 4 policies together and execute them sequentially. This wouldn't work because, when you get to the later policy, your initial state is kind of pretty bad already. So Renpei and Chen came up with this bidirection process where you can effectively chain those very different subtasks, sub-policy together. And this requires 2 steps for initialization and backward fine-tuning. I'll let Chen explain at his poster station today. Here I'm just going to show you some results. So here we want to teach a robot to build a simple structure. It has 2 red pieces. On top of that, we want to put a yellow piece. So you can see that this is a really long horizon problem that contains very different tasks, right? There's a search, there is a reorient, there's grasp, there is insertion. And you can see the sensors we have here. We have a top-down camera, which is only used at the beginning when you're searching the piece you want. And then after that, we use a wrist-mounted camera, which you can see in the bottom row there. That's what a robot sees. We don't have tactile sensor. That's something we really hope we will have in the future. Yeah, that's very important. So dexterous hands are also anthropomorphic, which is a really great potential because it opens up the possibility of train a robot directly from human data, right? We can collect humans, we can just imitate humans' movements and then train the robot to reach the similar dexterity. But this is also hard in reality, right? Because we need to have a system, we need to collect large scale and diverse data. That means we need to go outside of lab. We need to have a system that allows us to do that, to collect data in the wild. And there's a potential retargeting issues between the hands and the human hands and robot hands. So this is a brand new project we just started. We built a dexterity capture system analogous to motion capture system. We want to be able to collect the data in the most natural settings so people can wear them wherever they go, whole day long, collect a lot of motion capture, dexterity data. And once we have a large data set, and that's the beginning of training our robot to reach human level dexterity. And thank you for listening. So I can take a couple questions if you have any. Mark?
How close are we to the robot playing the piano? Karen, how close are we to the robots playing piano like that? Like, is that an easy or a hard task?
It's
compared to grasping?
It's a very, we don't know yet, but we believe that if you want to play natural like that, you do need a lot of human data, and not just any human data. It has to come from expert human data. And you know, the piano, you can argue that's a very kinematic motion, right? So the dynamic part is probably not as tricky as like playing Lego insertion, those kind of things. But just the kinematic part is very tricky because you are so many degrees of freedom you have to control, and the timing is really important, and the touch. So tactile was something that we also think it will be very, very crucial for this task.
Hi, good morning. My name is Alex Bayen. I'm really excited to be here today. Thank you for the invitation. Today I'm going to talk for 6 minutes about the Mega Vendor Test, which is a name we gave to what we believe is the largest mixed autonomy test on a short stretch of freeways completed since automation of vehicles started. What is mixed autonomy? Mixed autonomy is a world in which some automated features of vehicles interact with humanly driven vehicles. And in a world before everybody has a Tesla, this type of paradigm will have to operate in a framework where you have extremely bad communication networks. At best, you can rely on 4G LTE, maybe, and some local automation of vehicles without much information. So the question is, how do you get a small percentage of vehicles to interact with a large percentage of human-driven vehicles to achieve collaborative tasks? And one of the tasks we've been interested in is the removal of stop-and-go traffic. At this symposium last year, I told you we would do it with 100 vehicles, and today I'm going to show you the results. And here, what's happening is essentially, this is not a traffic jam. This is just humans being very bad at driving, like all of us, because of the lack of anticipation and the desire to catch up. So these instabilities you see here, they're not happening because of excess demand, oversupply. They're just happening because of bad driving. So 6 years ago, we started a framework which was the first integration of reinforcement learning with microsimulation on the cloud. It was the beginning of a new era when you could do this at scale. Kathy Wu, who is now a professor at MIT, is the one who created that framework. 5 years later, we implemented this on board a variety of car platforms. And more specifically, what we implemented is a reinforcement learning algorithm that can run in a completely decentralized fashion where the learning happens in simulation on the basis of real data, and then it's interfaced with a lot of the layers that are in the car that are really problematic for the algorithms. And the fact that if you run on multiple platforms, on some of them you can control car acceleration, on some of them you can control speed targets, on some of them you have access to all the onboard avionics, so radar, radar, you name it. On some of them, you cannot see anything, even though the car can see, you can't. So you have to infer what it's doing through the adaptive cruise control. So this reinforcement learning framework that we have created enables to learn through this variety of platforms. And then the way it works is there is a cloud-based, which is the layer you see on top of this slide, which broadcasts very high-level planning commands from data that can be obtained through feeds, name your Google traffic or INRIX traffic, and then broadcast it to the lower level that runs the local algorithms. Last November, we ran it on 100 vehicles, different vehicles. So we have 3 different automakers, 3 different architectures, 3 different frameworks. And what I'd like to show you in the next 3 minutes is essentially first how we did it and then what we collected from it. How we did it, it was kind of interesting. We rented a factory and then essentially established our own workshop where we built 100 radios that we deployed in the cars and mounted everything, unplugged a bunch of wires in the vehicles, and created an architecture to ship algorithms online to the vehicles. Lots of fun for the students to do. What it looks in the car is not glamorous. It's really just a Raspberry Pi with a few other onboard components. But the nice framework of the architecture as shown is that you can ship algorithms in real time and update them. We hired about 150 drivers because it's still not level 5. It's really just longitudinal control. So we would brief them in the morning, then tell them what you have to do as a driver is very simple. Just turn on the ACC, as you would do, the cruise control, and just be aware it's not going to do what you're expected. It's going to do something different, which is essentially wave smoothing. So from a user's perspective, it's just ACC, but just be ready that it might not feel like normal. Then we send them on different routes, and essentially we run this for about a week, and this is the way it used to look every day. So essentially it was like managing an airline with 100 aircraft, except it's vehicles, and sending them on the freeway, which amounts to about 1% penetration rate when you look at the amount of traffic it creates, and essentially have them work collaboratively, except they can't talk to each other. They can just talk to us through the cloud through a really bad connection, the cell phone network. And as we were doing this, we had built the largest video camera monitoring platform to our knowledge in the world. This is the i24 Motion. Just to give you a sense of the data it collects, I think the largest other testbed we're aware of is Sadigh in Germany, which collects about 25,000 vehicle miles traveled every year. NGSIM at Berkeley was 1,800. This is 200 million. So it's like orders of magnitude above, and it generates the largest data set in the world on traffic data, which I will show. This is what it looks like at a very, very, very close level. So every dot is the position of a vehicle every couple of seconds. Color encodes speed, green is fast, red is slow, and then the white vehicles are the self-driving vehicles. And the reason why they cross each other is because there's multiple lanes, so car don't fly over each other. To give you a sense of the magnitude, for a full day of experiment, this is what it looks like. The red things are essentially the big waves I was showing before, and nobody has seen data like this before. It just didn't exist last year when I spoke at this symposium. It's the best data there is in the world in terms of accuracy, in terms of coverage. And so what we're doing now is we're looking at the data we've collected for 1 week of experiment last year with the 100 vehicles to assess how much of the savings we're performing. And the beauty of this is that if you look at the savings per vehicle, the red bar shows that self-driving vehicle saves about 10%-ish energy for themselves, fuel, but the cars behind save even though they're not participating. I'll be done in 30 seconds, I'm sorry. The other things which are interesting is also you can see the variance of the speed on the freeways decreasing behind it. And finally, just my last picture, if you really want to look like at the low level of the trajectories, you can see the black trajectories behind the blue are essentially much smoother, and that's what this technology does. And with this, thanks, I'm out of time. Thank you. Yeah, okay, so on the safety side, we don't override the safety filters of the car. This thing has to run upstream from it. And then, of course, the outcome is that it's known that if you reduce variance in speed and acceleration in freeways, there's a correlation with decreased safety. So the outcome is also hopefully positive for safety. Thank you.
Thank you. Good morning, everyone. So speaking about safety, I will talk a little bit about my work on AI safety for autonomous vehicles. Now, the premise is that, of course, AI, and in particular machine learning models, are clearly ubiquitous in the different modules of a modern autonomy stack, from perception all the way to prediction, planning, control, and so on. AI models, however, are not perfect. For example, they might not have enough semantic understanding to reason about a situation whereby we have a car on a trailer, or they might get confused by auto-distribution objects, such as an aircraft on a road. And these are all real-world examples that have caused trouble. So to increase the robustness of AI models, along with the confidence that we place into them, my research on AI safety for vehicles autonomy targets how we design AI models, how we deploy them, and how we maintain them throughout their life cycle. Specifically, we work on design time assurances, whereby we develop techniques to robustly train AI models, along with techniques to calibrate the uncertainties that are produced by those models. Complementary to design time safety assurances, we work on deployment time safety assurances, where we design monitors that constantly monitor AI module to see whether there are any anomalies in order to trigger, in case of an anomaly, for example, a contingency maneuver. And finally, the product lifecycle level, we work on techniques to evaluate model performance, along with techniques to retrain a model throughout its life cycle, depending on interesting cases that are seen at deployment time. Now, I argue that such a multi-pronged approach is really needed in order to achieve the level of safety needed for safety-critical systems. Now, in this talk, I want to focus on the particular task of anomaly detection. So basically, the task of reasoning about unknown unknowns that can be seen at deployment time. And we've worked extensively in this topic, but in this talk, I want to focus on a specific class of anomalies, which I refer to as semantic anomalies. And concretely, let's look at this video from a Tesla dashboard. So first is nonsensical. We have an endless stream of lights, traffic lights, that are spawned by a truck. But now you understand what is happening. There is indeed a traffic light on a truck that is fooling the detection system on the Tesla. And here is another case that is causing trouble. So there is a stop sign printed on a billboard that is detected as a legal traffic stop sign that is causing a ghost brake that is not only an inconvenience, but also a safety hazard. So the interesting thing about these cases is that at the object level, you can't really see that the detection module has been misbehaving. This is really a malfunction, a system-level malfunction that stems from the unusual combination of in-distribution events. We refer to these anomalies as semantic anomalies. Now, while it might be very difficult for the designer to reason about semantic anomalies by hand, the claim is that all that an autonomous vehicle really needs is a little bit of contextual understanding to reason about these cases. And to this, we turn to the emerging capabilities of foundation models, specifically large language models. Here we have recreated the first scenarios in Carla, where we see the traffic light on the truck that causes the autonomous vehicle to stop in the middle of the road. And we have explored the idea of using a general purpose object detector that parses the scene in its components. And in particular, it detects that there is a truck carrying a traffic light. Then we use this information with an input template. You can see that it is quite long, that incorporates various best practices for worm starting. So this is the input to the large language model. And then what we get as an output is that some components of the scene, like for example the tree, are classified as absolutely normal and benign. But for example, in the bottom left, you see that the truck on the traffic light is classified as anomaly. Not only that, but the model also provides an explanation about why this could be a problem. So if you look at the answer to question number 3, can the vehicle drive safely in its presence? The answer of the model is no. This could deceive the vehicle into interpreting the traffic lights as a legal traffic signal. So this is very interesting and promising, and we have used this methodology in other settings, for example, in a robotic manipulation setting. But of course, these are still very preliminary results. First, as you might if you're familiar with the topic, large language models can hallucinate explanations. So we're working on the techniques to better ground the output of a language model in the capabilities of an autonomous system. On the other hand, not all hallucinations are necessarily bad. We can think of hallucinations as a plausible extrapolation of a training set that can be used in order to augment the training data to build a more robust model. Of course, on the horizon, we have vision language models, and of course, in image is worth 1,000 tokens and even more. So we plan on using actually vision language models as our interface to the scene so that we can bypass an object detector. And of course, the anomaly detection idea that I've just presented is complemented with all the other ideas that are more traditionally used in the AV industry, basically the more traditional runtime monitors, and we plan to explore such complementarity. So this work is just one example of a much broader program that I have the pleasure to lead, which is a program on safe aviation for future autonomy, and there are many people at Stanford and also Berkeley that are involved in this program. So if you're interested, please check out our website. And with that, we end my talk, and I'll be happy to answer any questions.
Are relatively slow to execute, right? So how long does it take you to detect these anomalies? I mean, you have like millions of frames and things, right? So is that a fast
Yeah,
process?
of course. But on the other hand, there are a lot of new techniques, for example, for distillation that would, in principle, really allow you to do this in real time on the vehicle. So yes, more work has to be done, both on the trustworthiness of these methodologies and in terms of their real-time computation capabilities, but we do see a path.
Cool, thank you. Okay, hi everyone. It is a big pleasure to be here. It's really nice to see everyone. What a joy to get to do this again. I have limited time and Ying was really chasing me. So I wanted to take this opportunity and just talk a little bit about the things we were interested in my research group, which is specifically thinking about how we design aerial robots. I always see bars as an opportunity for me to talk about building robots and not just designing controllers for them. And I want to do that again today. So we're interested in thinking about UAVs, autonomous aerial systems broadly. And of course, what's interesting about these to me is that they tend to have very complex requirements that trade off from one another and have really strong trade-offs. And I think it's a lot of fun and interesting to think of these as co-design problems. So I want to create a system and I want to simultaneously design the mechanics of the system as well as the intelligence for it, rather than having one person design a robot and then shipping it to someone else to design a controller. So this little cartoon here sort of tries to illustrate that idea. And I want to just today take the opportunity to describe two vehicles that maybe sort of scratch this itch for me. The first is we spend a lot of energy thinking about systems that avoid collisions. We have really sophisticated algorithms to detect objects and plan routes around obstacles, etc. But if you allow yourself to just collide with the world and be okay with it, it opens up a lot of interesting possibilities. So sort of motivated by this, a few years ago, we started working on this Tensegrity aerial vehicle that you see here. This is the latest iteration. That is designed to be really robust. So this is something that we can crash into concrete walls at like 8 meters per second, and it just sort of bounces away from it. What's nice about this is now you can really sort of free yourself from this constraint of being smart by just being tough, in a sense. And if you create these systems, of course, there's a lot of analysis in the background about finite element modeling, things like this. So to try and understand how you trade off the size, again, and the strength of these components, since it is a very coupled problem. But the end result is a vehicle that has some fun capabilities. So here you will see the drone, not a drone in this context. We're not allowed to fly drones on campus. This robot hopping across campus, and it's doing this with no information about the environment at all. So there's no knowledge about the information. It's on a ledge here that's maybe around 3 meters above the ground. And it's hopping. And because it is able to sort of survive these collisions, it can just operate in sort of very natural way using very simple sensor data. And one of the things we are motivated by is, if you have a wildfire event or something like this where there's a lot of smoke, for example, that might be occluding your sensors, you still want to be able to move through this to see if there is someone on the other side, for example. And with a system like this, you can really do this, right? So even if I I'm willing to put in the work to create obstacle avoidance detections and all of this, it might be useful to have this property. And this video just sort of shows a cartoon of this vehicle, again, not flying, hopping through campus past some trees. It has no knowledge, so it collides with things along the way, but it is still able to move from one point to another point, exploiting this collision tolerance. And here it's using only the inertial sensor. So you can put this vehicle in any sort of conditions with smoke, with anything, none of your sensors need to work. The inertial sensors will always be there. And this allows us to continue operating in this way. The second thing I want to talk about, I think I mentioned last year, is this morphing vehicle we've been working on. And here, we're very interested in efficiency when we're flying. This is one of the big constraints. It's always the energy capacity of your systems. And if you have a typical hover-capable vehicle, they have the problem that when you're trying to fly at speed, they tend to be pretty terrible at this. Like, just the geometry doesn't seem to work well. So we've created a system that can change its thrust direction, so you can produce the thrust in the forward direction to overcome the drag without tilting the body and thereby creating a huge drag surface and negative lift. With a sort of somewhat complex Rube Goldberg-style mechanism, but I think it's kind of fun. Again, it's a very mechanical solution to this problem. So rather than having a lot of actuators, what we do is we have a passive hinge with a spring, and then this hinge allows this mechanism to rotate the thrust direction. And by rotating the thrust direction, the force of the spring changes in a way that you have a sort of click-click bistable, like a pen, a click-click pen, bistable sort of configuration. And this gives us a vehicle that, with only the 4 actuators that you have in a normal system anyway, can change from a normal drone's configuration to this tilted configuration. Of course, when you're hovering, that doesn't really make sense. But the point is, in this tilted configuration, we can operate much more efficiently. So we can fly much faster, we can fly with much lower drag, so much longer range, much better efficiency, etc. And what I want to emphasize in both of these is we're not doing anything, thank you, particularly sophisticated in terms of the controls. Rather, we try to offload this into the mechanism, into the mechanics of the system. Of course, on top of this, you also want to do sophisticated estimation controls, etc., to leverage these capabilities and to then get more. But with the design of these systems, you have many, many degrees of freedom that otherwise remain untapped. And this can make your problem much easier to solve if you allow yourself to explore this. And then, as always, just want to thank the people that actually did all the work that I get to talk about. So Clark, Jerry, and Shangyu especially, and our funders. And with that, I will yield my 2 seconds. Thank you.
Question?
Yeah.
No.
Yeah. Thanks.
Okay,
as you scale up, is it harder or easier to be durable? And then if it's harder, do you see that being a challenge for making a hopping robot that could jump into a fire and save a person or put it out?
So the scaling problem is a great question, and we spend a lot of energy trying to answer it. The answer is it's a little fuzzy. So there's some argument we can make that it gets better. There's an argument that it'll get worse. I think the devil will be in the detail. Certainly at some big enough scale, everything becomes challenging, and it probably is not as sensible, right? If you're starting to carry a human or something like this, it probably does not make as much sense. But around the scale, from the size we have to maybe 1-2 meters diameter, it is not clear if it gets better or not. And I forget the second part of the question, but maybe you can find me afterwards.
That was the full question. Thanks.
Right, thank you. And thank you.
So thanks to Chelsea and Mark for organizing, and pleasure to be here. My name is Claire Tomlin. I'm a professor at UC Berkeley, and in a similar strain to Marco's group, we do a lot of work in thinking about safety and safety critical systems. And what happened? And thinking about how to integrate learning into safety critical systems. So we have been working on this for a long time and focused mainly on aeronautics applications. And these have become really very different and exciting in the past 5 years. From kind of traditional air traffic control. I love including that diagram to the left because it's from Alex's PhD when he was a PhD student here at Stanford. I used to be a professor here. But the introduction of drones like zip lines, medical delivery drones, Joby Aviation. So one of the students, Jason, in our group worked for Joby over the summer, and that's an amazingly interesting control problem, but also problems that, go away from aerospace into particular marine environments, and Marius Vigert is going to talk today in one of the sessions about that project. But in all of these, there's a kind of control stack, and Marco talked about this too, where you have the kind of pieces that could be automated or under human control, but we tend to separate these into this perception, prediction, planning, and control. And traditionally, our lab has been working on safety filters that take that actuation signal and ask, is it going to maintain the constraints associated with the system? So is it going to keep the aircraft inside of its aerodynamic flight envelope? Is it going to maintain collision avoidance with other vehicles, et cetera? So one of the recent projects we've been working on, which is really just kind of focused in that local area of safety filter with the aircraft itself, not thinking about those other modules, is one that that Jason has been working on. And this is inspired by this project with Joby. How do you automate the transition for an eVTOL aircraft from vertical to basically conventional forward motion? So this is done in the air. It's a safety critical maneuver where you're actually rotating the rotors of the aircraft while it's in flight. And this is exciting because there's not really good aerodynamic models, and it's a wonderful opportunity for gathering data and learning from that data. So we've been computing using safety filters. We developed reachable set technology that allows us to characterize the safety of a control law, or have basically a filter, like we talked about, coming in and guaranteeing that the vehicle stays within its aerodynamic flight envelope even while transitioning. The challenges we're going forward, and I think this is what a lot of us are thinking about now, is that these systems, the automated systems, are not operating in a vacuum. They're operating as part of a system of other vehicles, human interaction. And the modules, in particular perception and prediction, are best represented or best developed using learning-enabled components. And so in terms of what we're doing, we're really thinking about how to design those modules, perception and prediction, so that they interface with the safety filters. We've been working for a number of years now. This is under the DARPA Assured Autonomy program with Boeing, where we've been working on taxi tests and flight tests, where they've taken that Cessna aircraft that I showed, instrumented it with cameras, and they're doing taxiing and landing. So one of the first projects we worked on with them, and this is with Anish, who's here today, is thinking about how we might treat uncertainty in perception as kind of a first-class opponent, for example, if you're thinking about collision avoidance. And in particular, thinking about open categories, so training a perception neural net, but recognizing that there's objects that it can encounter that it's not necessarily trained on. But by coupling pixel level uncertainty with typical models of agent motion, like in this case, this is not an aircraft. This is just looking at a Waymo data set and pedestrians that are moving around that the system is not necessarily trained for. But we took that algorithm and ran it on board a Boeing vehicle that was moving around the runways, tracking other vehicles on the runway. And interestingly, that neural net wasn't trained to track other aircraft, but it was asked, could it recognize the uncertainty of a object moving around and be able to recognize that that is something that it should be tracking and track that. Thinking finally about prediction. So again, a module where we are going to be using learning-based components or learning-enabled components. So predicting, as an agent moving around in an environment, predicting the behavior of other agents. So here, the work that we've been doing, and this is a flight test that we are working on for deployment with Boeing next month, is trying to understand with calibrated uncertainty if the aircraft is coming into land and there are vehicles that are on the runway, can we predict whether or not those represent a runway incursion, or they will be when the aircraft comes into land. So we've developed this pipeline which takes as input the output of a learning-enabled component and then uses a sequence of statistical analyses, basically a quantile regression that's computing a confidence interval, and then a conformal prediction module which takes that confidence interval and calibrates it using the data that the neural net was trained on, and then passes that through a reachable set to be able to understand, again with calibrated uncertainty, the motions, predicted motion of the other vehicles with a probabilistic guarantee associated to it. Okay, so we're running that module in my 0 seconds next month. And I think I'll end just with saying that a lot of the focus that we've been doing over the years has been to think about automating platforms. And I think as we move further and further into, automated systems, and you've seen this already this morning, how do we think about taking some of this technology and really thinking about system interaction, systems in closed loop, the fact that we as an agent in that system are affecting the other agents around us. So with that, I'd like to thank a whole bunch of students and former students who've worked on this. Several of them are here today. I see them all sitting at the back. So, and thank you. And I'm happy to take any questions or just end because I know I have negative seconds.
I have a question. You mentioned deployment with Boeing. I'm curious if you can talk more, and you can use this mic while Dorsa sets up. Can you talk more about that? Is it going to be like a warning system for humans or something else?
Yeah, so Boeing would like to develop a capability to fly aircraft using onboard cameras and other onboard sensors using learning-enabled components. So they would like both a monitor to make sure that basically the learning-enabled component is working as expected, as well as some kind of statistical guarantee that which is associated to taking the uncertainty associated with those learning modules and propagating it through that uncertainty through the decision-making loop. So some kind of statistical guarantee on safety for those.
All right. Hi, everyone. Good morning. So today I want to talk a little bit about some of the work that we have been doing over the past year in the space of interactive robotics, and specifically taking a lens of modern NLP and large language models and thinking about how robotics would change in that world. And specifically, we have been thinking about this idea of what would it take to build something that resembles a robotics foundation model. And we have done a little bit of work in that space. So Sid is here today, and he's done a lot of work in the space of building visual pre-trained representations, this Voltron model, which was actually in collaboration with Chelsea, Percy, Tom Kohler, who I think is here today, Suraj, and Annie. So this was more of a work that was trying to really tap into offline data sets and try to train these visual representations that can kind of act as something, a pre-trained representation that could be fine-tuned for downstream tasks. But actually, the thing that today I want to talk about is not that perspective of what would it take to build something that resembles a foundation model. And specifically, I want to take a different perspective, which is that these foundation models, large language models, vision language models, they exist, and we could find very creative ways of using them. And I think that perspective is pretty interesting. I was personally initially very dismissive of it, but I think I've kind of come around and realized that there are many interesting ways of using them. And I think our initial attempt in that was for reward design. So if you think about learning human preferences, interactive learning of human preferences, prior to these kind of body of works, the way we would approach these problems was by active learning. So actively, we would ask these questions, these informative questions from people, and try to learn what their preferences are. And about a year ago, right before ICLR last year, Minay came along and she was like, oh, maybe we should ask large language models. Maybe they have the answer. And again, initially, that seemed a little strange that if we are looking at, let's say, a game, a negotiation game, like, we could try to solve it by supervised learning, or we could try to solve it like in a game theoretic way using reinforcement learning, but all of these approaches were failing at something. And the thing that they were failing at was they were failing at capturing human values. They were failing at being fair or being polite or being human-like. And what Monet was suggesting was maybe we should just ask a large language model, and maybe that has enough context to act as a reward function. And again, we were very unsure initially, but that ended up working out really nicely, especially in this domain of negotiations. So the idea here was we were training a reinforcement learning agent by calling a large language model within the loop. And the output of the LLM was acting as a reward function, as a regularizer that was kind of guiding this policy. And every single time like we would do that, we would generate a new policy and a new prompt. We would change the prompt based on that new policy, and again, try to get the feedback from the LLM. There's quite a bit of work that has like built on top of this idea, especially like recently. I think this week we had like 2 works in the category of using LLMs and VLMs as reward functions. In a follow-up work with folks at Google, we looked at this problem in the space of robotics. So the idea is very similar here. We are starting with a language instruction, a high-level language instruction, like it is late in the afternoon, make the robot towards the sunset, and that actually creates weights. The language model generates weights of a reward function that once you optimize it, it gets the robot to turn. And you could do things like sit down like a dog, or move your paw. My favorite example is do a moonwalk. You could say do a moonwalk, and it would generate the weights of like how a robot should do a moonwalk. But I think in general that was pretty surprising and interesting that, again, LLMs can work really wonderfully as reward designers. And building on top of this idea, it turns out that one of the challenges is really the perception side of things. Can we actually describe the scene to the level where we could actually like answer these common sense reasoning questions? And one of these common sense reasoning questions that we're always interested in is like, how is it that the human realizes very quickly they should clean out a table that looks like this with children's Legos, but if you ask a human to clean this table, they know that they should not be taking apart the Legos, right? Because this is a very intricately built Lego. I spend a lot of time building these types of things. A human cleaner will not do that. And the question that we were interested in is, why is it that humans are able to do that? Can we get any AI agent or any robot to kind of like distinguish between these? And again, today, if you describe the scene to the level of detail that kind of like describes what is going on, an LLM has that knowledge, has that rich context that can answer these common sense reasoning questions. So in this work, Monet will be actually talking about this in her poster session. What we are looking at is using a VLM and LLM and using active perception to actively guide question answering, actively ask questions to try to get as much information from the VLM to be able to answer these common sense reasoning questions. Kind of moving along, I'm going to very briefly talk about a few other works where we are looking at semantic manipulation. So here we are again using an LLM along with a key point model. So this is work that Priya has looked at. And the interesting thing here is now we could refer to object parts. So for example, when it comes to like picking up an item, you can say you could pick it up from the eraser or from the middle, or we could say pick up the hammer from the left or from the side. My favorite example are the stuffed animal ones. You could say, hey, can you pick it up from the nose or from the arm or from the belly? But again, like this is very much like powered by the fact that we are using an LLM, and that allows us to train this key point condition policy, which is much more efficient than what prior work would do, and that allows us to do semantic manipulation. Finally, one last example that I wanted to mention is in the space of teaching. So, for example, when it comes to teaching people how to do motor control tasks, corrective language is pretty powerful. So, for example, you might say hit the ball at a lower angle. And the question is, again, can we generate these types of corrective language using a large language model? So what Megha did here was she took trajectories from student and from an expert and a fine-tuned large language model that would actually generate corrective language to teach humans, to kind of like close the loop and actually teach humans. And the interesting thing is that the language as generated is ranked higher in some settings compared to the reference language, because the language model says things like glide gracefully to the left, as opposed to, let's say, like the reference, which just says right hand down. And we've kind of like looked at this in a number of domains, including like exercise domains and steering domains. I know I'm out of time, but one last quick thing is this idea that so far every example I have shown is looking at LLMs and the fact that they have a lot of context and semantics. But they're actually much more powerful than that. And one thing that they're really good at is identifying patterns, very abstract patterns that are not even semantically meaningful. So in a recent work, this is again at Coral this year, what we have been looking at is kind of like passing in the end effector, the end effector location of this robot, again, very abstract, just numbers, to the context of a large language model, and then ask an LLM to continue that pattern. And this particular like sine wave pattern, the LLM actually like generates robot trajectories where the robot is able to continue that behavior and actually like finish the task. And if you give it rewards, trajectories along with rewards, you would actually be able to do some type of optimization that looks a little like RL, but it's basically like in context learning, you provide trajectories and then you would be able to get a trajectory that is high reward and is able to do this task. All right, so with that, I'm gonna thank the group and I'm gonna just stop here.
Hello, great talk. Yeah, so this is definitely really interesting. I was wondering, it seems like a lot of the works, minus that last one, are relying, as you said, on LLMs having a lot of context, knowing what things look like, and maybe even reasoning about intentions in terms of the Lego case, right? But I think a lot of works have found that like they're not always the best at producing actions or reasoning about actions because they weren't really trained on that. Do you have any thoughts on that, if it's necessary, or if we can just continue these sorts of methods?
I think, yeah, so I think that's a very good question. And that is like literally like two paradigms. Like, do we want to take a modular approach and try to like reason about things and then move the action part to a separate policy? And that seems to be the more reliable paradigm, but I have a lot of hopes in terms of like these models being able to actually output actions. And you're seeing some promise with that with works like RT2, for example, which is a vision language action model that's actually putting out actions or generating robot code. So I think it would be very interesting to see if we can train them, given that they're so good at recognizing patterns, if you could train them to actually put out actions.
Got it. Thank you so much.
One quick note, if you're standing by the door, please just come in. There's actually lots of seats along the side and near the front, and it'd be great to make sure that anyone can come in if they want to. Great. Thanks, Grace.
Good morning, everyone. I'm Grace Gao from Stanford University. First, I would like to thank Mark and Chelsea for organizing this workshop. I know there are a lot of work behind the scenes. Okay, so today I'm going to talk about our research on autonomous vehicle localization using GPS, from Google Decimeter Challenge to GPS on the moon. So I guess we are all like, oh, first of all, I want to thank the key contributors to this talk, and Daniel, Mira, Shrub, Ramya, Kadai, Marta, Guillaume, Alana, Tara, Derek, Easy, and Adam. And then Daniel and Kadai, they will have lightning talks and poster sessions. Okay, so I guess, you know, we are all like GPS users from our smartphones, and then maybe many of us also use GPS to, you know, navigate and find this auditorium. However, GPS is still not a solved problem. And in particular, Google, since a couple years ago, they put out the Google GPS Decimeter Challenge, and they have been doing that every year, and there's one going on this year as well. So basically, they called the whole community to try to, you know, better solve the urban problems for GPS. And so far, I think over 1,000 teams worldwide have participated in this Google GPS Decimeter Challenge, including our own team. As we can see in the urban environment, the satellite signals can be blocked by the buildings and then also reflected by the buildings. So the issue is sometimes you just don't have the signals, right? And what to do if you do not have signals? Actually, no signal is also signal. What does it mean? So here in this illustration, as you can see, if you can have the signal reception from the green satellite, like you know that you are in the area with the satellite visibility. However, if you do not see the other satellite, if that satellite got blocked by the buildings, you actually have the knowledge that you are in the satellite shadow of that satellite with respect to the building you are next to. Then we can model all these, the shadow area, out of the shadow area as zonotopes, and then we can use like the intersections of the zonotopes and do zonotope shadow matching to utilize the information that no signal is also signal. And then for this, we actually need the environment, right? We need to know where the buildings are. So for that, we utilize the recent tools in computer vision called NURFs, or neural radiance fields. And then we create neural city maps for the urban environment. And then with this nice like a neural representation of the maps and then the 3D environment, we can better analyze how the satellite signals interact with the environment. So, that was about the GPS for the Earth users, and we are also exploring the moon. I don't know how many of you have heard about Artemis mission. Maybe some of you, cool. So the US is going to send 2 humans to the moon surface again. And then, last time any humans explored or went to the moon, that was during Apollo times over 50 years ago, right? And then, as a matter of fact, the first step, it was the Artemis 1 mission towards this landing 2 humans again on the moon. And then it was launched the end of last year. And then it was a mission of over 3 weeks. And then the total distance traveled was 1.4 million miles. And then for exploring the moon, especially the moon surface, and then the current method, it uses map matching. And then for the vision-based method using map matching, this is dependent on the lighting conditions. And then what's more, the resolution of the map on the moon, especially in the polar areas, is not that great. So our question is, can we set up a GPS-like system for the moon, but with much lower cost? And then, so for that, our group, we have been developing the lunar navigation satellite system. We don't want to, put a very expensive system there, just like the Earth GPS is actually quite expensive. So our approach to lower the cost is to use smaller satellites, as small as shoe boxes. In comparison, the terrestrial GPS satellites, they are as large as trucks. And we want to use much cheaper clocks, like 1,000 times cheaper than the atomic clocks on today's GPS satellites. And then our key idea is to utilize the terrestrial GPS for the lunar navigation satellite clock and the firmness correction. So that means if your lunar orbiting satellites, once they have the visibility of the terrestrial GPS satellites, they can utilize that information to calculate the time clock time offset or the firmness corrections. And this is still a very challenging problem, mainly because, as you can see, this is in the moon inertial frame, right? All the colorful, the traces, they are the GPS satellite orbits. And then you can see the satellites, they have bad geometry for the moon users because they all coming from the same direction. So our group, we have been developing a lot of advanced filtering, signal processing methods for utilizing the terrestrial GPS satellites for the moon. And then I also want to talk about quickly 2 missions. So we are participating in. One is we want to send out a robot swarm on the moon, and then this is in collaboration with NASA JPL. So next spring there will be 3 small robots exploring the moon surface, and this is a part of this cadre mission. And then in addition, there's this another collaboration with NASA JPL about the endurance mission concept. And for that, it's really a long-range autonomous driving, so over 2,000 kilometers of autonomous driving in the South Pole area of the moon. And then for that, for any NASA mission, there are always the communication satellites to relay the data. And for that, a lunar pathfinder satellite is scheduled to be launched in 2025. And so for our work, we are trying to leverage this communication satellite, the Lunar Pathfinder satellite, to utilize that for also helping with the navigation and positioning on the moon. So I think I'm out of time, so thank you so much.
Okay, great. Thank you, Grace. That's the end of our first faculty talk session. Next, we're moving on to 4 sponsor talks. These are just short 1 to 2 minute talks, and then from there we will move on to the student spotlights. If you're a student that's presenting in the first session, please start to line up along the side so that you can be prepared to give your very short lightning talk. And also if you're a sponsor, please be ready to come up on stage. The first sponsor talk, I believe, is by Gadik. Yeah.